Just as in the scalar field case, it can be shown that any observable quantity that we might be interested in, any matrix element, can be written in interaction picture as a time-ordered product of several fermionic fields. These fields will of course depend on which process you want to study. E to power minus I d4x, the interaction part of the Hamiltonian, divided by, well, basically the normalization. And when written in terms of Feynman diagrams, it can also be shown that this is actually equal to just the numerator but when calculated using Feynman diagrams, only the connected diagrams should be taken into account. Of course, when our strategy of evaluating such matrix elements will be, again, just to Taylor expand this exponent, and then we will have the time-ordered product of many fields. And this time dependence of these fields are determined by the non-interacting theory. So at the end of the day, we will have to evaluate terms like many products of fermionic fields. And of course also there will be some barred ones. And also keep in mind that when you are making an actual computation, you have to take into account that you have to be consistent with the ordering of these operators, because if you just change the order of two of the fermionic degrees of freedom, then you get a minus sign, which should be correct. Well, this brings us to how we can calculate this time-ordered product, and we can write this as a path integral. In fact, this can be written as deep psi, or all these fields, psi I1 x1, psi I4 bar x4, and the e to the power I times whatever action we have. So this will be in fact a fermionic path integral, where these psi and psi bars are just Grassmannian numbers. And let me also add the normalization, proper normal, to make sure that it is properly normalized. Now, we are basically following what we had done in the scalar case. So let's first define the z of j as a deep psi bar, exponent I. We have the interacting theory, the non-interacting part of this theory, d4x, psi bar, I del slash minus m psi. Let's also add some source terms, psi plus I d4x, j bar of x, psi of x, plus I d4x, psi bar of x, j of x. So here j itself is a fermionic field, a spinor field. So it has 4 components, just like psi, so that this product is just a number. And once we have all these quantities, the above matrix element can be written as so this matrix element, time ordered product, psi I1 x1, psi bar I4 x4, will be just to obtain a psi, we just need to take the functional derivative with respect to j bar. So this will be minus I functional derivative with respect to j bar of I1 at the point x1. And for this, for psi bar, we just need to take the derivative with respect to j. So minus I functional derivative with respect to j I4 at the point x4 of z of j. So we take all this derivative and then divide by z of j is equal to 0. Because essentially that is the numerator over here. So let's look at z of j. How can we simplify z of j? Now, again, just borrow z. Let me rewrite z of j. This is the fermionic path integral again, just like in the case of the scalar field, we will, by just shifting these psi fields somehow in a suitable manner, we will try to write this in a form z of 0 multiplied by some function that depends on j. We are trying to find this function. Now, also another point, you see here, these we said that it is important the order of these fields, and when you convert them to derivatives, it's also important the order of these derivatives, because you can change the order of the derivatives with respect to Grassmann variable numbers, but when you change the order, the derivatives also acquire a minus sign. They are anti-commutative. So to simplify this derivative, this path integral, we will basically shift psi of x. So let me write psi of x as some different psi of x plus d for y, g of x, y, now let me choose the minus sign over here, j of y. So let's see what this function is, if we will be able to simplify this expression by a suitable choice of this g. Now let me just look at the exponent, not the whole expression, because that is what I'm trying to simplify. I already know that this measure will be invariant, so this under this transformation, this measure of the path integral just becomes epsilon x psi bar of x. Now we know this because at every point x, this is just a constant independent of the field, so it doesn't change the measure. Now with this change, we have the exponent is e for x epsilon bar minus d for y, j bar of y, g tilde x, y. I will just write what g tilde is. I del slash minus m epsilon bar minus d for y, j of g of xy, this is not bar, times j of y plus d for x, j bar of x, psi of x minus d for y, g of xy, j of y, and plus d for x psi bar minus d for y, j bar of y, g tilde x, y, j of x. Now again, here let me just define what this g tilde x, y is, well, you see, psi is a column matrix, and epsilon, and hence epsilon is a column matrix. J itself is a column matrix, so that here in this exponent is psi bar j and j bar psi are just numbers, and G over here is just a square matrix, and this G tilde is defined as a, you see, we obtain G tilde when we convert psi to psi tilde, psi bar, but psi bar is just psi dagger multiplied by gamma 0, so it's J bar. So this is just gamma 0, G dagger, x, y, gamma 0. Now, what we want is, in this expression, we want to get rid of all expressions that are linear in psi. So, for example, we have here psi bar psi, that's an expression we can keep, but if we take psi bar here, and this term over here, that's a linear term in psi. Similarly, here we have a linear term in, let's say, psi bar. So we would like to choose G such that we get rid of all the terms linear in psi or psi bar. So let's see, terms linear in psi bar. So we get those terms, for example, when we take this term from this parentheses and this term from the second parentheses. So there's a minus d4x. Well, in this term there's a d4y integral. Let me also put it over here. d4y. There's a epsilon psi bar and a g of xy, jy. And furthermore, term linear in psi bar appears here, plus d4x psi bar of x, j of x, which we can also write as d4x psi bar of x minus d4y. So here there's also this operator which I forgot to write. So here we get I del slash minus m, but keep in mind that these derivatives are with respect to the space-time point x, not y. So here we get I d slash x minus m d for y, g of x, y, plus, now here there inside there is j of y plus j of x. We want this term to be 0. Well, in the path integral we are summing over all possible psi bar fields. So for all possible psi bar fields this expression should be 0, but that tells me that this parenthesis has to be 0. J of x should be equal to I del x bar minus m d for y, g of x, y, j of y. And furthermore, since j is something arbitrary, and in fact we are taking derivative with respect to j, meaning that we are changing the value of j and looking at how z changes, and so this equation should be satisfied for an arbitrary j, but that tells us that I del x slash minus m acting on g of x, y, this should itself be Dirac delta, 4-dimensional Dirac delta x, y. So this is one thing that G should satisfy. Now let's also look at the psi term, the terms linear in psi. Let's see if this will give us a new equation for G. Well, let's see, the terms linear in psi are this one, this term over here, and we take the psi over here, so let me write it, d4x. Now let me try to copy it from here. There is a d4x. here there is the psi of x, this derivative with respect to x. And the other term linear in psi is this one over here. Plus d for x j bar of x psi of x. We also want this to be 0 if possible. Now let's see, in order to be able to simplify this expression even further, note that here we have the derivative of psi, but we can get rid of the derivative of psi by doing an integration by part. So this will become d for x. Now it became plus due to the integration by part, d for y, j bar of y, g tilde, x, y, I. Now let me keep the minus 1 over here and write the minus del x, del slash x, but this time the derivative is acting on g tilde itself. Well, I cannot just move this to the other side. I have to first separate the derivative and the gamma matrix. I would rather keep the derivative also here, keeping in mind that it is acting on everything on the right, whereas the gamma matrix in this that's the slash is on the derivative is acting on the left, the gamma matrix is on the right. There's a I minus m plus j bar of x psi of x should be equal to 0. So this again tells us that since this should be 0 for all psi of x, this is psi, this term in the parentheses should be 0. So j bar of x should be equal to d for y, j bar of y, g tilde, x, y, minus I del x slash minus m. So this equation should be satisfied. And of course, for this equation to be satisfied for an arbitrary j, this term over here should be a Dirac delta. Now let's show that this equation is actually nothing but the previous equation we have, so everything is consistent. But to show that, first let's take the matrix Hermitian conjugate. You see that it might be confusing because here we have a matrix and the derivative operator. I'm just taking the Hermitian conjugate of matrices, not the derivative operator. And well, since I'm taking the Hermitian conjugate of matrices, then this minus I also becomes I. So I, now when I take the Hermitian conjugate, which contains the transpose changes the positions, so it's I del x slash minus m. This time the derivative is acting, now here the derivative is acting on g. Now the derivative is still acting on g, it's just the matrices has changed their position. So this is g tilde x, y Hermitian conjugate. This should be equal to Dirac delta 4 x minus y. Now let's look at this term. And okay, there is also the Hermitian conjugate of the gamma matrices over there. Now we know what the Hermitian conjugate of gamma matrices are. Let's also remember that g tilde is gamma 0, g dagger gamma 0, and hence g tilde Hermitian conjugate, matrix Hermitian conjugate is gamma 0, g gamma 0, since gamma 0 conjugate is just gamma 0. So let's continue. This is over here we have I. Let me take the gamma 0 out, del x slash minus m gamma 0. This whole thing is this parenthesis over here. Then this g tilde Hermitian conjugate is gamma 0, g of x, y, gamma 0. This is equal to the Dirac delta of x minus y. And well, we are almost done. You see, this is 1. Let me multiply by gamma 0 from the left and gamma 0 from the right. So gamma 0 from the left, gamma 0 from the right. This is also 1. This is also 1. So I del slash with respect to x minus m g of x y is equal to, well, this is just a number over here. Gamma 0 squared is 1, so this should be equal to Dirac delta 4 x minus y. So we see that as long as this equation is satisfied, if we shift our integration variable in this way, we eliminate all the terms in the exponent that are linear in psi or psi bars, and that is what we wanted to achieve. Now let's look at what remains. Let me take all of this expression. Terms that are not linear in psi. d for x psi bar I del slash minus m psi. So this is this term and this term. Then we have this term and this term, these two terms. d for x. Well, there are two minus signs, one minus here, another minus over here, that makes plus. d for y, j bar of y, g tilde x y. Well, I'm taking this one, but keep in mind that this I del slash minus m acting on this one gives me a Dirac delta, and that Dirac delta, when I integrate this integral, just gives me j of x. So here I get j of x. Now let's continue. I have the terms that are, well, from this term I get a term linear in psi. I have this one which is not linear in psi. So I get minus d for x, j bar of x, d for y. There is the d for x here, d for y over here, j bar of x, g of x, y, j of y. Let's continue further. There is this term over here, minus, again there's a d for x integral, d for y integral, d for x, d for y, j bar of y, g tilde x, y, j of x. And you see that this term cancels this term, so the exponent just becomes d for x psi bar I del slash minus m psi minus d for x, d for y, j bar of x, right, okay, there's just one of these, g of x, y, j of y. So let's go to z of j. This is now the measure over psi this time. Exponent of I d for x psi bar I del slash minus m psi minus I d for x, d for y, j of x, gxy, j of y. But you see, this exponent is now independent of psi. So I can just take it out. So we get exponent of minus I d for x, d for y, j bar of x, g of x, y, j of y, multiplied by something that doesn't depend on j. So if we set, but that something is, when we set j is equal to 0, the only thing remains is that something else. So that is actually z of j is equal to 0. Well, there is one point that we need to pay attention to. Is here I use this property of the Grassmann variables. I eta bar eta plus b ib I some constant times, let's call that j bar j, where eta and j are Grassmannian numbers. This is equal to exponent I eta bar eta exponent I b j bar j. Well, I just treated these numbers, these Grassmannian bilinears, since there are two of them, these Grassmannian bilinears, as if they are just commuting numbers. But you see, they are commuting actually. Let's look at, let's calculate their commutation relations, n bar n and j bar j. Well, I'm just using systematic, a shorthand notation. Here we have many integral over x, etc., but it doesn't really change our argument here. This will be eta bar eta, j bar j, minus eta bar eta, no, minus j bar j, eta bar eta. So let's see, this is plus eta bar j bar eta j minus eta bar j bar eta j. So this is just 0. But you see what I have done in these two terms. Eta bar is on the left hand common, j is on the right hand common. Inside I have eta j bar plus j bar eta, the anti-commutator of eta and j bar being Grassmannian numbers, they anti-commute, so these two terms give me 0. So I'm left with this term and this term. So let me also add one more term over, add and subtract. Let me add eta bar j bar, no, let me add or subtract j bar eta j and add j bar eta j. You see, this term and this term, they have the same eta j factor at the right. On the left we have eta bar j bar plus j bar eta bar. Again, it just gives me 0. So these two, when I sum them up, they just give me 0. So now j bar is at the front. Well, I can do the same trick. I can just exchange eta and j. So let me just write it minus j bar j, eta bar eta, plus, if I exchange their position, I will get a minus sign, they anti-commute, minus j bar eta bar j eta. And if I just commute these two things one more, the eta bar and j, this becomes a plus, this is minus j bar j, eta bar eta, plus j bar j, eta bar eta, but this is 0. So bilinears commute, and physical quantities, in fact, will be made up of bilinears of these spinors. So you see, when we were discussing the Dirac field, we imposed the anti-commutator, but when we are looking at the causality of things, the causality will be determined by the commutators. But what commutators we want? We want the commutators of observables. The field itself is not an observable, but the observables will be constructed by bilinears of the Dirac fields, and for bilinears we can talk about the commutators. And we didn't show it, but we can show that actually things will be causal, just like in the case of the scalar fields. So now we know this relation z of j. Okay, let me just write z of j is equal to z of j is equal to 0 multiplied by this exponent. Again, although I have anti-commuting objects, I'm just changing their position as I wish, because each one of z of j equal to 0, and this exponent contains bilinears of Grassmann numbers. So let's first look at the psi I1 of x x psi bar I2 of y. We had already calculated this, so we know what this is. And at the same time, this is minus derivative with respect to j bar I1 at x, and minus I functional derivative with respect to j of I2 of y of z of j over z of at j is equal to 0. You see, this doesn't depend on j, so when we use this expression z of j is equal to 0 term, it will just cancel. So this is actually equal to minus I, the functional derivative with respect to I1 bar of x times the functional derivative ji2 of y of this exponent. Well, let me just use the coordinates z1 and z2, j bar of x, g of xy, j of y. No, it's not xy, z1, z2. Let me start with the first derivative. This is minus I functional derivative with respect to I1. And okay, I forgot to write before. And when we evaluate this, we have to put j is equal to 0. So this is this derivative will bring down a factor of one of factors of this. So j of y, I will take the derivative with respect to this one. And let me just show it, minus I, this minus I over here, and then I have another minus I d4z1, d4z2. Now you see I'm just commuting this functional derivative over a Grassmannian variable, so I get a minus sign j bar of z1 and g of z1 minus z2, the functional derivative of z of j of z2 with respect to j at y would be Dirac delta to the 4 y minus z2, and I have a minus 1 because this derivative, which is itself a Grassmannian operation, anti-commuted with this one. And also note that these are all spinors. I'm taking the derivative with respect to a particular component. So let me write this as I take the L component of this, and then the L component of j of z2. So if I take the derivative of the L component with respect to the I2 component, I also get an additional factor of Kronecker delta L of I2. And then I have the exponent. Now let's see, this minus 1 cancels this minus 1 over here. I have a minus I, and there's another I over here. They also cancel. And eventually I will put j is equal to 0. And this will be equal to, let's see, well, if this derivative can act on the exponent, but it will also bring another such term which contains j, but when set j is equal to 0, it will just give me 0. So I have to act this derivative on this j over here. So let me first write this as m component of that one, and here I have the ml component. So this will be equal to minus I d4z1. Well, z2 derivative I evaluated. Now if I take the derivative of functional derivative of this j of z1 with respect to this, I get a Kronecker delta I1m, this one over here, Then there is a four-dimensional Dirac delta of z1 and x, and I have z1 of y, because I took the z2 integral using this Dirac delta, and I have the mi2 component of this one because I summed over L using this Kronecker delta. Now I can do the similar thing over here. Now I put j is equal to 0, the exponent is 0, the additional exponent is 1, the additional term just disappears, and this is equal to minus I g of x y, I1, I2. So now we know what g is. This is I1, I2 is just I times this term, which we had already evaluated. Now we can continue like this. For example, I will leave it as a homework. If we have time ordered product of, let's say, psi I1 of x1, psi I2 of x2, psi bar I3 of x3, psi I4 of x4. Just show that this is equal to 0. Well, let me just copy all of it. Let me have 3 of them. Now this is also bar. Well, I will not have 3 of them. There is this term. And there is also this term. So again, it's just like all possible non-zero contractions. So this is, let's say, homework 1. Homework 2, well, this is actually kind of trivial. This term this is equal to 0, and similarly if they are barred fields. Now the easiest way to see this is if you just go over our previous computation over here. You see, if these are both psi fields, for example, then both derivatives are with respect to j bar. There are no derivatives with respect to j. So if both derivatives are with respect to j bar, or let's look at if both of them are barred fields, both of them are with respect to derivative with respect to j. There is no derivative with respect to j bar. So here this would be a derivative with respect to j itself, this would be a derivative with respect to j, but now you see the first term doesn't contain in j, it contains j bar. So if both of these fields are barred fields, then here there would be a derivative with respect to j itself, not j bar, but that would mean I have to take the derivative of this exponent, again, not this term. But if I take the derivative of the exponent only when I set j is equal to 0, this j is equal to 0, meaning j bar is also equal to 0. So these terms, both of this term will be just 0. So just fill in the gaps. So this essentially proves that we have the Wick theorem for the fermions also. Also pay attention to the fact that here I am not, I keep the ordering fixed, so we can go one more step. So this will be equal to 0 time ordered product of psi I1 of x1, psi I4 bar of x4, order product of psi I3 of x3, psi I4, or no, I2 and I3 of x3. These are what these contractions mean. Now note that to be able to write these fields in this form, I took this operator, commuted it with this field and also this field. So every such commutation under a time ordered product, even if it's under a time ordered product, it brings a minus sign. Since there are two minus signs, the sign didn't change. But in the second term is just this expression, I1 x1 psi bar I3 x3 psi I2 x2 psi, now here this is bar, psi bar I4 x4. Is it to bring the ordering of these fields into the ordering that appears in this term, I first have to exchange these two operators, but that means I have to put a minus sign over here. So this is something that you need to pay attention to when you are taking the contractions. Just pay attention to the ordering. They will lead to some minus signs.